Babbage Difference Engine number 2, serial 2. Okay. The first 3 words are Babbage Difference Engine. Babbage was the name of the gentleman who designed this machine. And that photograph of him over there in the center panel was probably taken sometime maybe 10 years before our Civil War, but it was over in London, because he lived in London. Based on his age, I'm able to guess that that's what the time frame was. The third word in that title is engine. Now, you probably all have a concept of what an engine is, but let me give you my definition. An engine is something that relieves you from having to do the work. So a good example would be Fred and Barney used to go out, the Flintstones, they used to go out to their vehicle, they'd get into the vehicle, they put their feet all the way down to the ground because there were no floorboards. They grabbed a hold of the sides of it and they ran with the vehicle. They were the engine. Okay? But if you could put a gasoline-powered motor or an electric motor or something like that in there, then they could have put their feet up and let the engine do the work. Well, this is an engine as well, in the sense that it does mental work, it does calculations, and it does them rather rapidly. What we're calculating, you'll see in just a moment. Now let's get to that middle word, Babbage Difference Engine. Can anyone tell me what the term difference means in the context of that title? What does the term difference mean? That's close. It's mathematical, but you're in college level. Go all the way back to grammar school. What did you first learn in grammar school?
Subtraction.
Addition and subtraction. And subtraction had a result called the difference. So this is the difference, the result of the subtraction. Okay? Now, subtraction of what? Well, that's what this machine is all about. This thing solves polynomial equations that you learned in high school, powers of x equations. Okay, but it does it rather rapidly. It does one complete calculation of a new result about every 8 seconds. Let's take a look at the blackboard over here, and I'll show you what it's doing. Now, everyone can sort of murph around. It's too bad we couldn't put this up on the real feed. Hopefully you can see it. There's an equation at the top. It's x cubed minus 2x squared plus 1. 2x squared plus 1. When you put x equals 1 in here, 1 cubed is 1, 1 squared is 1, so we end up with 1 minus 2 plus 1. And when you do the math of 1 minus 2 plus 1, you get 0. So the first result is 0. With 2, you get 2 cubed is 8, 2 squared is 4, times 2 is another 8. So we have 8 minus 8, which is not plus 1. So the next result is 1. For 3, it's not equal to 2. We had 0, we had 1, we don't get 2. You get 3 cubed, 27, 3 squared is 9, times 2 is 18, 18 plus 27 is 9, plus 1, you get 10. And then 33 and 76 and 145, you get this column of numbers that you see in the first column, the result column. Now, this is where the difference comes in. You take the difference of consecutive results, one from another. So you subtract 0 from 1. If I take nothing away from 1, what do I get for an answer? 1. So they write that over here in this first column, this column called the first difference. Take 1 from 10, you get 9. 10 from 33, you get 23. 33 from 76, you get 43. You get the second column of numbers. Everyone with me so far? Okay. Yes. Now these numbers turn out to not just be a random set of numbers. They are the result of another polynomial equation, which is written down at the bottom of the board. 3x squared minus x minus 1. So since this is the result of the polynomial equation, we can do exactly the same thing. We can take its differences. So if you take 1 from 9, you get 8. 9 from 23, you get 14, and so on. And we get this column of numbers over here, which turns out to be 6x plus 2 is the equation. You can easily show that 1 times 6 is 6, plus 2 is 8. 2 times 6 is 12, plus 2 is 14, 3 times 6 is 18, plus 2 is 20. That's the equation 6x plus 2. Now, since this is the polynomial equation with this result, we can do the same trick of taking consecutive results. So 8 from 14 is 6, 14 from 20 is 6, and so on, we get 6. Now it doesn't matter what x is, the answer is a constant. Now we can go one step further. Take 6 from 6, you get Okay, so the diff 4 column over here would be 0. And everything to the right of that would be 0. So now we've completed the table. This is called the difference table. I'm now going to ask you to give me a value from 1 to 4. 3. Now Reed's laughing. Since the end of July, I have only gotten 3 as an answer. I don't have any other cards in my pocket. Now, out of 1 in 4 chance, why do I get 100% 3? I don't know. Okay, but here's what happens. Babbage, I can take the third row, and I'm going to get down so you can see it. And watch what happens. If I add 23 to 10, what will 10 turn into if I add 23 to 10? 33, the number below it. Add 20 to 23, you get 43. Add 6 to 20, you get 6. Add 0 to 6, you get 6. So the third row produces the fourth row. The fourth row will produce the fifth row. The fifth row will produce the sixth row. And on we go, getting more and more results, and we're not doing any multiplication. We're just doing addition. Pretty clever, huh? Okay. Now Babbage realized that if he was going to build a machine that was 100 columns wide, a result in 99 differences, because it's an x to the 99th equation, he's going to have to do 99 consecutive adds all the way across one row to get the row below it. And he couldn't build a machine to do that. So he came up with a way of being able to do this thing in only 2 adds, not 99. He does, in fact, out of the 99 adds, he does about 50 of them simultaneously, and the other 49 simultaneously. 2 sets of simultaneous adds. Now, where are the sets derived from? Well, he derives them from odd and even columns are added together, all at the same time. And then, using the results in the even columns one step down, when you add even the odd columns all the way across. Then it looks like this. Can you see over there? Probably not. I'm going to use the 6 and the 8 and the 9 and the 1. Add 6 to 8 and add 9 to 1, and what do you get as a result for both of those? 14 and 10? These two numbers that you see below it? Okay, so now we have 0, we have the 0 over here next to the 6, we have the 14 and the 9, and we have the 10. Now do the even columns to the odd columns. So add 0 to 6 and add 14 to 9. And you get 23 and 6. So now we have a 10, 23, 14, and 6. We started up here, now we're down here. You can repeat the process. Add 6 to 14, 23 to 10. Simultaneously, you get these two. Add 0 to 6 and 20 to 23, you get those two. And that wouldn't matter if it was 100 columns wide. They would get exactly the same thing, but you'd have to have all those staggered steps all the way up. Okay? That's a pretty simple thing to do. So he could build a machine that would do that, and he knew it. This one is doing it. But it's 8 columns wide, not 4. This is the constant on the very end of a 7th order polynomial. This is the result. So they have results, the first difference, the second difference, the third, the fourth, the fifth, the sixth, and the final difference, the 7th difference. This one will be added to this. At the same time, we'll add this to this, we'll add this to this, and this to this. And they'll all happen together. Okay. Now, when I added 6 to 8 on the blackboard over there, I did not erase the 6. Because I needed to have it there to add 0 to 6 on the next step. But on this machine, how am I going to add this column to this column without doing something to move them? And the answer is I have to count one of them down to 0. It's called a destructive read. So I'm going to read the number all the way to 0 and transmit it through a gear that joins the 2 over to the other column where it's going to count up. So one side counts down, the other side counts up. Okay? Now once we've destroyed it, we have to get it back. But the gear in between knows what that number was because it was transmitted through that gear. So it actually has the value on it. We lift it up 3/16 of an inch and we put it back to its original position. And the result is that the odd column which counted down now gets restored back to its original value. And that lifting up separates from the even column so that we don't undo the add. The add has been finished, we separate from it and leave it alone. And we reset the odd. Then we lift the gear up again, one more time, and it separates from both. No longer connecting odd to even. But now the rack between the even and the odds drops down, and we do the count down the even, count up the odd, lift it up 3/16 of an inch, reset the even, lift it up 3/16 of an inch again, and go back to the first side, drop it down and start all over again. So you're going to see the odd column add to the even, reset the odd, and you're going to see the even columns add to the odds, and then you're going to see the reset of the even, and you're going to repeat the process. And one of those processes takes 8 seconds. Read is now going to get, you're actually going to see it. Here we go. So there's the add. Now we're going to do the reset, and that's happening all the way across. This is the even to the odd, resetting. And now we're going to add and reset, and then add and reset, and that's happening all the way across. Meanwhile, of course, the result is being produced, and the result gets transmitted to the printer, so we actually get the answer to be printed. Okay. We are at 135. X is 135. We started out at x equals 0. And the equation that we are doing is this one. 8x to the 7th plus 2x to the 6th plus 9x to the 5th plus 5x to the 4th plus x cubed plus 7x squared plus 4x plus 41. And we're up to x equals 135. Now I have a computer printout of every 5th answer. And the 135th one is right about, my thumb is pointing right here. Would you like to hold this? I'm going to read off the result column. This should be the result. Ready? 65502328685072281. Who says yes? Meaning that Babbage has just proven our computer came up with the right answer. Or is it the other way around? They're both the same. So who's right? They're both right. Okay. Now, if I go through another 5 calculations, we'll be at another step. We started out, actually, at the very, very beginning when we had 0. We just had a 41 here. Now we're up at the 135th answer, and it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16 digits long. This thing can go up to 32 digits. So we can get very large answers on here, okay? And it doesn't take long to get to them. This was used to do something very important, which gets to the point. What's the point? Why was this machine ever designed? And the answer goes back to what happened with Babbage. Babbage was born on December 26th in 1791, the only son of a rich banker who was able to afford to send him off to college, Cambridge, and he learned to be a mathematician. He got his degree, basic bachelor's degree in mathematics. Unlike most other people, he did not pursue any further degrees. He left college at that point. Well, he didn't really leave. At some point, he was actually elevated to the chair of the Department of Mathematics and became the head person, something that was only been shared by a few people, like recently Stephen Hawking and Sir Isaac Newton, just to give you a couple of examples of people who've held that position. But in this position, it also gave him an opportunity to do something he really liked to do, which was form intellectual societies. And he went around and hobnobbed with all the rich and famous and intellectual people of his day, like Charles Lyell, the geologist, Charles Darwin, Charles Dickens, a lot of guys named Charles, just like him, and somebody named John Herschel. And Johnny came to him one day and says, "Charlie, I got a problem. I'm in the astronomy club, and we ran out of our astronomy tables. So we went to a publisher to publish new ones, and he ran out of materials. So we ended up having to go to another publisher to finish the job to get the total number of tables we need. And now we have these 2 sets of tables from 2 separate publishers, and I don't know if they match." Would you be willing to verify them with me? So Charlie agreed, and one night John comes over with these two books, and they go through them, and they begin to find discrepancies between the two. And they get to one particular page that has so many discrepancies that just annoys Charlie to the point where he stands up in a loud voice and exclaims, "My God, I wish these values had been executed by steam." In other words, get rid of the human element in the development of these tables, mechanize it. Well, what was the human element? Turns out he had a library with 300 volumes of mathematical tables, sine tables, cosine tables, logarithm tables. But there were a lot of government tables too. There were navigation tables by the ships for the ship's captains, and construction tables for bridges and building, and actuarial tables. He looks through them and he sees they're all being done by this method called the method of differences, using polynomials that actually fit the curve that you're trying to produce, okay? And all that work is being done in France by unemployed French hairdressers. It's a men's guild that's been put out of business probably by the French Revolution. People don't have to have their hair done because they don't have any more head. The guillotine. So they're retrained to become computers to compute these tables. And it's pretty easy to verify that their work is correct. So it wasn't the mathematics of the difference that was the problem. The problem was that these result sheets that they produce are given to typesetters to set up the movable type to print the books. And he's working right to left because he has to turn the plate over upside down and put the movable type in from one end to the other, right to left, while he's reading left to right. So he's reading and putting type in and coming back and reading some more and putting type in, and he's losing his place in what he's reading, or he's putting sixes in his nines. There's all kinds of reasons for him coming up with a page that's wrong. Put it in the printing press, and every book published has all these errors. Okay? A different publisher probably gets different errors, and that's exactly what Charlie was seeing. So he realized he could actually build a machine that would do the typesetting, but he couldn't actually have humans feed it because they would end up doing the same problem that the typesetter is doing. So he had to compute the value itself. This is what the engine's going to do. And he can't afford to do any of that. So he goes to the British government and he says, "Did you know that your tables are full of errors?" And they said, "Yeah, we know. What can we do about it?" And he said, "Well, I can build you a machine which will produce flawless tables. There will be no human intervention." That sounded pretty good to them, so they decided to fund his project. Okay, so in 1823, he hires the best blacksmith in London, named Joseph Clement. He starts designing the parts and giving the designs to Joseph, and Joseph starts making the parts. And 9 years go by. Now it's 1832, and the British population is asking, "Where's our difference engine? Where's the difference engine?" And they're getting kind of antsy about it. So Charlie goes over to Joseph and says, "Listen, take some time off and build me a little 3-column version of the big machine that we're building, or designing." Basically, at this point, I haven't even started putting it together yet. Build a little 3-column version and give it to me, and I'll demonstrate it to my friends in my soiree so they'll know that it actually will work. So Clement takes 6 months off, builds this machine, gives it to Babbage. Babbage shows it off. Everyone knows, okay, this is going to work. We can understand what it's doing. And then the British government hears about it, and they thought the machine was ready. So in 1833, they come to Charlie and say, "Okay, where's our machine?" And he said, "Oh, it's only half done." Half done. What's the whole? "Oh, the whole is 24,000 parts. We only have 12,000 parts made." "Listen, it took you 10 years to get only half done. Is it going to take another 10 years to finish it?" He said, "Well, I hope not, but it could." "Well, you better finish this project pretty quick or we're going to pull the funding." Now, they had already spent 17,000 pounds over those 10 years on this project. And to give you an idea of what that means, that's 34 people's salary over the entire 10 years. Do that with today's population. Go out and get 34 people, add up their salaries over 10 years. That's approximately how much it cost the British government. In those days, £50 a year was the typical British salary. £1 a week, 2 weeks vacation. Okay. So at this point, he goes back over to Clement. He says, "Look, the government's breathing down my neck. I want you to move your shop over to my side of the Thames River so we can basically get the job done much quicker. Oh, and by the way, I can't afford to pay you to make the move." Well, that was the last straw for Clement. He basically announces to Charlie, "I quit." He's no longer going to work for him. Well, the interesting thing about that problem was the British law says whoever made the parts owns the parts. And Clement made the parts. So Clement's going to keep all the parts, but the British government steps in and says, no, Charlie designed them, so you have to give some of the parts to Charlie. So he gives him a smattering of parts that are of no consequence, keeps all the important ones, keeps all the tools because they're his, keeps the part of the design that he's still working on. What's Charlie got? He's got the beautiful fragment, he's got the rest of his design, and he's got the smattering of parts. That's it, and they part ways. Now Clement looks at all this precious metal and decides it's not doing him any good in that form, so he melts it down and uses it for something else. And that actually puts the axe in the entire project, and the British government pulls the funding. Boom, project over. Nothing built. Nothing other than the beautiful fragment. Well, Charlie's not deterred. He turns to a whole brand new project. He starts designing something that's 5 or 6 times bigger than the difference engine. He calls it the analytical engine. And he works on that for the rest of his life. But around 1847, he realizes he could have economized on his original difference engine. Instead of taking 24,000 parts, he can get it down to just 8,000 parts. So he spends 2 years redesigning it. He calls it difference engine number 2. He comes up with very complete designs because he's not giving them off to anybody. He's just working on designing it. Goes to the British government and asks them if they would build that instead. And they said, resounding no. Won't do it. Been burned by him once, they're not going to get burned again. So he goes home, puts the plans away, keeps working on his analytical engine, and in October of 1871, just before he turns 80 years old, he dies. And his sons inherit all this stuff. And they don't know quite what to do with it. By 1875, they decide to give it all to the London Science Museum. Now the Science Museum can exhibit the beautiful fragment. They can exhibit the smattering of parts that he got, but all the design work for both difference engine number 1, partial, and difference engine number 2, complete, they put in the vaults in the basement. And they disappear from history. And they don't surface again for 110 years. Now, because of the size of the crowd, I'm going to divide you right smack down the middle. If you're a pair, stay together. If you're a family, stay together. But I want this group to go around to the back. And the rest of you center yourself in the front. You'll get a chance to go in back as well. So there's no reason to rush. Just half the group go to the back.